Okay. So last week we talked about network biology, and we reached this point where we were discussing um, the the analysis of the global topology of networks and how this global topology could be related with with the function that those networks of that system represented by those networks. And there are interesting hypotheses about why some networks are scale free or have the small world property that may be eventually related to the function, but it's always a doubt that we have if it is the structure of the network that is responsible for or is important for the function, or if it is a consequence of the process of formation or evolution of these networks. So it's an interesting area, but with it's difficult to prove any of the or to test any of these hypotheses. So I wouldn't say more useful, so it's not the right word, but more commonly applied are measures of local topological properties. So now the idea is not to evaluate the complete network or get an estimate for the complete network, but to understand how the different components of the network or different groups of nodes of the network are organized and what is the local structure of the network around each node, and that may help us to understand the relevance of that node to the whole system. And so most of these things that I'm going to talk now, some of those we computed them in the tutorial. So the centrality measures are there are a large number of different centrality measures, and the aim of a centrality measure is to rank the nodes in the network according to their relevance. Being their relevance may mean different things. So here the most common centrality measure is the degree. So the degree is the number of interactions a given node has. So we are assuming that if a node has a lot of interactions, that means that it has an important function. And in agreement with this is that theory that, for example, the scale-free networks are more robust to attacks or to catastrophes. The nodes with a high degree, if they lose their function or if they are attacked, they have a higher impact on the whole network structure. So that's the reason why nodes with high degree in some situations are more important. In biological networks, we have here a problem. For sure, a node with more interactions, it means that it probably is a node involved in multiple functions or in regulating other nodes. So it for sure is it's an evidence that that node, which in biological networks normally corresponds to a protein or to a gene, that node is relevant for the function of the system as a whole. But most of our networks, biological networks, are derived from collections of individual studies that have studied each protein or gene. And we have what is known as a publication bias, which means that some genes or proteins have a higher degree because they are important for the system. And because they are important for the system, they are more densely studied. There are more people doing experiments with those genes, and during those experiments, they discover that that gene or that protein interacts with a set of neighbors, and that will end up in the biological networks. So it's not that so we may consider that nodes with a high degree, in fact, are important nodes in the network, but that the fact that they are relevant in the biological system contributes even more for their high degree. So we have the notion that the biological networks that we use nowadays are incomplete. So we don't know every interaction that all human proteins or all proteins of any organism. So other organisms are probably, except for model organisms, there are a lot of organisms for which there is little information about their interaction networks. For the model organisms and for the human species, we have a lot of information, but still for the model organisms and the human species, the information about the networks and interactions is incomplete. So we cannot exclude that some of the nodes that nowadays have a low degree, eventually they will have a higher degree later on. Especially if someone finds that they have an interesting functions, if they are related to a disease or if they have a biotechnological application related with the function of that gene, then people will study it more, and by increasing the density of studies about a gene, you will get more interactions. So there's a loop that we must be careful using the degree, because sometimes we have inflated degrees just because there is previous knowledge about that gene or protein. Trying to circumvent this limitation, there is this eigenvector centrality. What is this eigenvector centrality? Maybe I'll try to write. So we talked in the last class about the agency matrix, right? The agency matrix is a matrix where it's a square matrix where each element tells you if element of the row I with the column J tells you that node I is connected to the node in column J, to node J. And these metrics, you can try to find their eigen vectors and eigen values. So that means that there are some vectors that multiplied by the agency matrix are equal to a value, a constant value multiplied by that matrix. So this is this pair, a vector and a value, are called eigenvectors. If you, this is a general property of any matrix. For some matrix, you have eigenvalues and eigenvalues and eigenvectors. And these matrices may have more than one pair of eigenvalues and eigenvectors. But using the eigenvector that corresponds to the greater eigen value, the values in that vector, there is a value for each node, and that value is called the eigenvector centrality. And the thing is that in this eigenvector, a node will get a higher score in that vector if it has a large degree, but also if its neighbors have also a large score. Okay, so these will propagate in so node A has a larger eigenvector centrality if their neighbors also have a high eigenvector centrality, and their neighbors have a high eigenvector centrality if their neighbors have a high eigenvector centrality. so the thing is that this is proportional to the average degree of the of the of their neighbors. So in this case, you can consider that the node is important in the network, not because he has a lot of interactions, but because he is connected to other nodes that have a lot of interactions. So that's the principle behind the eigenvector. Just try to erase this. And I have that mouse pointer problem again. Okay. Sorry. Yesterday we also computed the betweenness centrality. So the betweenness measures the importance of a node. If that node, so the nodes are more important if those nodes are part of shortest paths linking any other two nodes in the network. So generally, a node with a higher degree also has a higher betweenness, but there can exist some nodes, some bottleneck nodes that have a high betweenness and not so high degree because they are connecting different modules in the network. So the communication between nodes in those different modules must pass through that node. So these special nodes in bottlenecks may have a high betweenness, even if they don't have a high degree. Yes?
Something about the eigenvector. Ian?
Can you repeat?
I've got a question about the eigenvector centrality because it says it's the average degree of the neighbors. Then if a node is the neighbor of a node with a very high degree, and except for that doesn't have any other neighbors, it will have a high eigenvector centrality, even though it would seem not to be so important.
I'm not sure I understood all that you said. Can you rephrase that?
Okay, so I'm just thinking of an example.
Yes.
There's one node which has like a degree of, I don't know, 20 or something, so it's really connected. And one of its neighbors is a node which only is connected to this highly connected node. And that node will have a eigenvector centrality of very high because it only has one neighbor, and that neighbor has a very high degree, even though that node seems to be not super important.
Yeah, the thing is, you're right. So if these nodes, for example, if that node with a degree of 20 has a lot of nodes just with one degree, so it's a star with that node in the middle, then the fact that all its neighbors have a very low degree will push down the eigenvector centrality. Okay, so it is not obvious the effect of using this eigenvector centrality because we know that having more interactions will contribute to a higher degree, to a higher eigenvector centrality, but the quality of those neighbors will also influence the value of the eigenvector centrality. And it is true that some periphery nodes, if they are connected to very well connected nodes, increase their eigenvector centrality, but not as much as the one that has a lot of connections, if those connections are also not all periphery nodes. I'm not sure if I'm answering your question.
Yeah, I think
so you can imagine this relation that I wrote about the there is an eigenvalue that multiplied by the agency matrix equals the eigenvector multiplied by the agency matrix, and it's like you can imagine this as an iterative project, iterative calculation, where each node sorry, contributes to the importance of the neighbor nodes. So everybody imagine that you give each node has the power to distribute votes for the popularity of other nodes in the network, and each node will give their vote to their neighbor nodes. Okay, and you cannot do that only with one iteration, because if you do that only with one iteration, the values will not be converged, will not be stabilized. So you have to give the votes for every node. Every node will distribute its votes for its within its neighbors, and then there's a new distribution. Everyone has a different number of nodes now, of votes now, and they will distribute it again. And you do this until you have a steady state of number of votes in each node. I'm not sure if this is a good analogy, but it's how it works. So this relation, if you so if you separate these, I don't want to write again because I lose my mouse pointer when I write, but the equation that I wrote was a matrix equation. But if you represent that equation for a particular node, that would mean that the eigenvector scores must obey that situation where the eigenvector score of a node is a linear combination of the eigenvector scores of all its neighbors.
Okay. I think I slightly understand that. I also now see a little more the importance of this. But it would maybe not be that the eigenvector centrality would be one-on-one with the importance of the node, but it can give some like a very good insight still.
Yeah, the eigenvector centrality is also related. I don't know if you have, and we'll talk later about that other type of measures, is related with the Google PageRank algorithm. The algorithm that is behind the way that Google's originally ordered the pages after a search. And again, that's the thing. It's an iterative process where every node in the network favors its neighbors, or contributes to the importance of its neighbors. And so these weights can be obtained instead of doing the matrix calculation, doing an iterative process where the score of each node is an average, a weighted average of the scores of its direct neighbors.
Okay.
It is somehow correlated with the degree, but it gives extra information because it somehow characterizes if your neighbors are also important or not. That's the main idea behind the eigenvector centrality. So, but they are related in the sense that eigenvector centrality gives a lot of weight. So a node with more neighbors has a higher chance of getting a high eigenvector centrality because it has more neighbors contributing to its eigenvector centrality. So in some way, it is also like counting the degree, but giving a weight to each of the neighbors. And that weight depends on the degree of the neighbors and the weight of their other neighbors. So all the network structure will influence more or less locally the eigenvector centrality. the betweenus gives more importance to the fact that a node is an important information spreader in the network. So if it is located in a spot in the network where a lot of information passes through it, if you imagine that the network is a information processing system. Yesterday we also used the closeness centrality measure. That is here I wrote the mean shortest path length to all other nodes, but in fact it is the inverse of the mean shortest path length to all other nodes, because higher closeness means that the distance to other nodes are smaller. So here is just trying to identify the nodes that are closer to the center of the network. If you imagine that network with a lot of dots, and in the periphery we have the more not so well connected dots, so the closeness will for sure favor the ones that are in the middle. You also have eccentricity that we spoke earlier last week also. That is the but here to become so eccentricity, we defined it as the maximum shortest path length beginning from the node. But to be a centrality measure, so a centrality measure should have a higher value if the node is more important. We make the inverse of that original eccentricity. We also have this cat centrality that is also in part it is follows the same principle of closeness. So it wants to find the node that is linked to all other nodes with the shorter paths, but it doesn't use only the shortest path lengths. So it considers all paths to all other nodes, but the paths with higher lengths have a smaller weight. So it measures the number of paths of each length to any other node in the network, and gives more weight to nodes that reach a higher number of other nodes in the network with shorter paths, but not necessarily the shortest path. So these are all variations. Generally, as we saw yesterday, most of these centrality measures are positively correlated. So if a node has a higher closeness, it usually has a higher cat centrality, a higher degree, higher eigenvector centrality, and higher betweenus. Sometimes there are some nodes that are specialized in one of those centrality measures, like the bottlenecks nodes for betweenus. So you can try different approaches, or there are even algorithms that do like a global approach. So they compute several centrality measures, rank all the nodes in the network according to different centrality measures, and then they produce a final scoring or the final ranking that is like the majority voting of all the independent centrality measures. So if the node is well ranked in all measures, it is for sure in the top, but then every different centrality measure contributes to that global ranking. So that is the way to rank all the nodes. But we may be interested not in ranking the individual nodes, but in characterizing the relationship between different nodes in the network. And for that, it is useful to have a measure of similarity or of distance between two nodes, and that then once we have distance between two nodes, we can easily compute distances between groups of nodes. So the most obvious distance between a pair of nodes is...
There's a question in the chat.
Sorry?
There's a question in the chat.
Oh, sorry.
It is about the use case for the...
Okay. Well, the use is always the centrality measures are, all of them are used with the same thank you for pointing out, as I'm in presentation mode, so I don't see the anything about the shape. So all centrality measures are used with the same aim, that is to find the most relevant nodes in the network. The thing is that some people think, oh, the degree only counts the number of interactions and doesn't count if those neighbors are more relevant or not. So you have the eigenvector centrality. Then people say, oh, but I'm not interested in only in the number or interactions or the number of, or who are those direct interactors. I want to know if a lot of flow in the network passes through a node, and I have between us. Or I want to identify which is the node where I can more easily reach every other point in the network. So that's closeness. What was the other one before cats? Sorry.
Eccentricity.
Eccentricity. It's the concept of eccentricity is very similar to the closeness, but now we look at the other way. So we try to find which is the farther away point in the network, and then we make the inverse of that. So the closeness and the eccentricity, you can compare it like closeness is more like a mean. The eccentricity is more like a non-parametric estimate, because you don't count all the paths, you just count the one that is more farther away from the node. So these are different angles of looking at the same thing. And the cat centrality gives importance to the distances, but it's like I'm not only maybe let me think of an example. So a node is has very short connections with other nodes. So it has a high closeness. So short connections, short paths linking that node to many other nodes. So it should have a low closeness. But you can have two nodes with a similar closeness, but one of the nodes not only has very short paths linking that node to other nodes, but there are multiple redundant paths. So you can go from one node, from that node to the neighbor nodes through multiple different parallel, if you want, alternative pathways. And if those pathways are also small in length, maybe not as small as the shortest path, but they are short paths, then that is a positive thing for the cat centrality. It's not only counting the length of the shortest path, but it's evaluating also if I have more different alternative ways of connecting the nodes. So it tries to, the cat centrality, the eigenvector centrality, try to capture, and in a way between the centrality also tries to capture more information about the whole network structure related to that node in particular. But all the centrality measures, their aim is to try to find which is the most important node in the network, and you can look at it as trying to find the nodes that, if you take them out of the network, will change more the network properties. Or in biology, we use these centrality measures normally either to predict new proteins associated with a given phenotype or a disease, or within a group of cluster of nodes that we know that are associated with a phenotype or with a disease. The ones that have a higher centrality, we extrapolate, or I propose the hypothesis that they are more central to the mechanism of that phenotype. But I'm not sure if that was useful.
Yeah, I understood. I didn't get that from when you first explained cats, so thank you.
Yeah, so the idea of both cats and the eigenvector centrality is use more information about the neighboring environment. The eigenvector centrality tries to give importance to the quality of the neighbors, being that quality also dependent on the degree of those neighbors. Cat centrality, instead of looking only at the shortest path, it's like it gives more points to that node if it has multiple ways to reach other nodes in the network. That's it. But again, as with centrality measures, where we have the most simple centrality measures like degree and closeness, here when we are studying pairs of nodes, we have the more direct methods like the shortest path length, or what is called the topological overlap, that is the fraction of neighbors in common. This could be computed, for example, with a Jaccard coefficient, for example. So if you have two nodes, node A has 10 neighbors and node B has 20 neighbors. But if you make the union of those sets of neighbors, you only get 15 neighbors, because they have said 10 and 20, right? No, the union must be, for example, the minimum size would be 20, it is 25. Okay, you have A is neighbor of 10 other nodes, B is neighbor of 20 nodes. But if you make the union of those two sets of neighbors, you get 25 nodes. That means that five nodes are common neighbors of A and B. So the Jaccard coefficient for computing this topological overlap would be 5 over the 25. So it's a way to compute the fraction of neighbors in common. What distinguishes, there are different formulas to do that. In the Jaccard coefficient, you divide the number of common neighbors by the set of neighbors that are either neighbor of one or the other node, but you could have different formulas to compute this neighbor. Yeah, that's it. So these two ways of studying if two nodes are related or not are the most simple. But then we have some other more complex ways to define the relationship between two nodes in the network. One is what is called either node or edge connectivity, and we are going to explain it in the next slide. Or we can apply some algorithms like random walks, and we'll talk what is a random walk. Particularly, the most successful random walks are random walks with restart that are that are equivalent to the PageRank algorithm. And you can also apply network diffusion that has very similar properties with random walk. So in network diffusion, you imagine that there is some nodes in the network. So if you want to study the relationship of node A with node B, you imagine that you are injecting in node A, it's a source of material that is incoming into the network, and that material will spread through the interactions of A, and will continue spreading through the network until some of that material that goes into A reaches B. If A and B are very well connected, then a large amount of material that is introduced in A will get to B. So you simulate diffusion, you keep injecting material into the network, into nodes in the source networks, and then those materials will divide equally through all the interactions of node A, and then the process will repeat for all the across the remaining interactions in the network, and you count how much of that material gets to the sink node. That's a way to compute the relationship between two nodes. But in the end, it gives very similar results to random walks with restarts. But first, these edge or vertex connectivities. For that, we have to define cuts. So cuts are sets of nodes or edges that when you take them out of the network becomes unconnected. So you divide a connected component into two components. And the minimum cuts are the minimum sets of vertexes. When I say vertex, is equivalent to node. The minimum set of vertices or edges that you take out and separate the network into two components, and you can apply these for specifically to two nodes. So a vertex cut for two vertices, U and V, is a set of vertices whose removal from the graph disconnects U from V. So you have a pathway, at least one pathway that would go from U to V, and when you take those vertices out from the vertex cut, there is no way you can go from vertex U to vertex V. And so the minimum size of a vertex cut is what we call the vertex connectivity.
So a vertex is a node or an edge?
A vertex is a node. And
Okay.
the edge is an interaction. Sorry, in different books and different articles, you will find these different nomenclature. So nodes can be vertex for some people, but it's the same. So
and the
edges are interactions. And sometimes they are also called arcs.
Yeah, and so the vertex cut is the set of okay, I understand.
So I'll try to again. Maybe there is a network in the next slide. So for example, if I consider here a node 9 and node 12. So the idea is that what is the minimum number of nodes or vertices that I have to take out from the network to make impossible to go from node 9 to node 12. So that would be 10, of course. But if I take out 10, I can still connect 9 to 12 through this path from 8, 11, and then 12. So I have to take out the minimum. It would be 10 and 11, or 10 and 8, but is the same size of the set. So if I take out 10 or 11, then it is impossible to connect 9 to 12. So the minimum size of the vertex cut that separates 9 from 12 is 2. Okay, so the vertex connectivity of nodes 9 and 12 is 2.
Okay, thank you.
And if there is a similar concept, but for edges. In edges, I would have to take this edge, for example, and the most simple would be again to be 2. If I take this edge and this edge, 9 is not connected to anyone, so it is also not connected to 12. So the minimum set of edges that you have to take out of the network to make it impossible to connect node 9 to 12 is the edge connectivity. So this is if two nodes are connected by many different pathways, then their edge or vertex connectivity is higher, because you have to take out a lot of nodes until you are able to separate those nodes into different components of the network. But if those two nodes, for example, if I count the vertex connectivity between either 9, 10, 12, or 11 to another node in another part of the network, I just have to take out one node, because if I take out node 8, I cannot link 9, 10, 12, or 11 to any other of the nodes in the network. So in this case, the vertex connectivity is 1 between 9 and 5, or between 9 and 3, whatever the node. It's just necessary to take out one node, and the connectivity between 9 and the rest of this part of the network will be lost. So when you have these bottlenecks in the connection between two nodes, they have a low connectivity. If you have a lot of alternative paths connecting the two nodes, you have a high connectivity. And that connectivity can be measured in the minimum size of the vertex cut or the minimum size of the edge cut.
Okay, thank you.
Okay, so these measures are also ways to assess if two nodes are very well connected or are more unrelated in the network topology. And they carry more information than just looking at the shortest path length or looking at the fraction of common neighbors. The random walks, and in particular the random walks with the restart. It's like you can imagine, for example, that I have a walker. So imagine that is a map of roads in a country, and you have a traveler or walker that starts in node 4. And the random walk means that the walker is in node 4 and he has 3 possible direct destinations, node 1, 3, or 5. And he's going to randomly pick one. And if the network has no weight associated with the edges, so each one has the probability of 1/3 of being visited by the walker in the next time step. If the network has weights in the edges, then there is eventually those weights in the edges may make the probabilities of each one of the nodes to be visited different, okay, according to the weight. Imagine that he decided randomly to go to node 3. Now he has 2 options, 1 and 2. He takes randomly, picks 2. Then he has 3 options, 1, 3 again, or 8. He goes to 8, and so on. So if you make a simple random walk, it will go on forever. And that's a stochastic process going on in the network. And the thing is, if you do this forever, an infinite amount of time steps, and you keep recording, and you keep recording the frequency with each node is visited by the random walker in the long time. You reach a stationary distribution, and if you do this with an infinite random walk, it is possible to show, and you can check it computationally, that that probability of being visited by a random walker is proportional to the degree of the node. Okay? If you do that infinitely. So in this network, the node that would be visited more often would be, I guess, 8 and 5. Yeah. All the others have less than 4 degree. Those would be so that stationary distribution for an infinite random walk is not informant, because we already know the degree much more easily than performing a random walk simulation. So people have thought that if I want to know among all the other nodes, the ones that are more related with the source node of the random walk, I have to implement a restart probability. So a random walk with restart in the beginning, you have to set a restart probability, and imagine that you have a restart probability of 0.5. So 50% of chances are that at any point in the random walk, you get back to the origin of the walk. So you start in 4, and you have 50% probability of keeping in place in the 4, and the other 50% are distributed equally by the 3 possible neighbors. So you randomly pick one, so you have 50% chances of being in 4 in the next time step, and then you have 1/6, right? If I'm not, so it's 1/2 divided by 3, so it's 1/6. 1/6 probability of visiting 1, 3, or 5. And imagine again that you go to 3. Then in 3, you have 50% chance of getting back to 4 because it is the origin of the random walk. And extra, you have 1/6 because it also has 3 nodes, direct neighbors. You have an extra 1/6 probability of getting to 4, 1/6 probability of getting to 1 or visiting 2. And you do this iteratively. In each time step, you have 50% chances of getting back to 4 and 50% chances of visiting a different node. In this way, you can perform the random walks with restart and count how many times each node is visited along the random walk. And that probability of a node being visited in a random walk with restart is a measure of how that other node is related with the original node. So here you have a representation of the results of a random walk with restart. So the nodes in red have a higher probability of being visited, and it's, as you would expect, they're direct neighbors. And then as you get away from the source, you get lower probabilities of being visited. Of course, nodes that are at the shortest path distance from the source will have higher probabilities of being visited, but in random walks with restart, it also counts if you have more different pathways that can lead you to that node from the source, you increase the probabilities of being visited. And if those alternative paths are also short paths, that also increases the probability of being visited, because due to the restart probability, the walker doesn't get, it's more difficult to get farther away from the source, because after 4 time steps, it's very likely that you will get back to the source at some point. Okay. The nice thing about this random walk with restart is that you don't have to simulate the random walk. Okay? You can compute it iteratively again by defining a weighted agency matrix that is here represented. It is weighted because, so here instead of having 0 or 1 when the nodes are connected, for example, node 1 is connected to through 2, 3, and 4. So in the first line, I have node 1 connected to the second column, third column, and fourth column. Okay, so these are the 3 direct neighbors of node 1. Instead of having a 1, because it is connected, I have 1/3. So I divide the numbers in each line by the degree of the nodes of that row. And that gives me a transition probability. So I'm saying that when I am at node 1, I have, and if I'm going to walk and not return to the restart position, I have 1/3 probability of visiting node. I am at 1, I have 1/3 probability of visiting node 2, 1/3 probability of visiting node 3, and 1/3 probability of visiting node 4. And this is the same process for all the other. Actually, these I'm reading these in rows, but it should be read in columns. So you see here that for these 1, 2, 3, 4, 5, I have these different fractions. I shouldn't have different values here because the network is not weighted. I must read it in columns. Okay, so I divide each column by the degree of the node in that column, because when I am at this node number 8, I have 4 possible destinations, 9, 11, 2, and 5, and each one has 1/4 probability of being visited. And the thing is that I can imagine that I have a starting vector that is just all zeros and one in the position 4. And then to know the probability of being in any other node in the next time step, I can just multiply my starting vector by this matrix, and this will give me the probability of the node of the walker being in each possible node in the next time step. So this is a process. If you multiply a vector with the probability distribution of the position of the walker at one time step and multiply it by this matrix, you will get a vector that is the distribution of the probability of the walker position in the next time step. So if you do this iteratively, you have the previous distribution of the random walker, the vector with the probabilities. You multiply it by the agency matrix and get the next probability. But you have to multiply it by the restart probability. Actually, here this is C is called the damping. You can define the random walk in two different ways. You can define the restart probability, and 1 minus the restart probability is the damping factor. Here it is, C is the damping factor, so is the number that is multiplied by the probability of the walker times the agency matrix, and you have 1 minus C, that is the restart probability, multiplied by the starting vector. So with P restart probability, the next time step, the distribution of the walker is going to be equal to the starting vector. With the 1 minus the restart probability, in this case C, the next time step, you will have the distribution computed by the product of the present time distribution of the random walker position times the weighted agency matrix. Okay, so you can compute these iteratively, and normally with a few iterations, this achieves a steady state. So when you compute this equation again, the new random probability distribution of the walker is very similar to the previous one, and normally you define a stopping criteria if the differences between the random probability vectors are smaller than a very small number, for example 0.001, then you stop and you get the stationary distribution of the position of the random walker. Was that clear?
Yeah, but I have a doubt. Like, I understand this random walker concept for like where a person is placed, for instance, or the state of the system. But how does it translate into biology in terms of proteins and genes?
Yeah, so this is just used as a way to compute the strength of the relationship or similarity between nodes in the network. So in biology, you can use some analogy. For example, if you are analyzing signaling networks. Okay, if you imagine that this is a signaling network, so each node is, for example, a protein that is able to phosphorylate other protein, and that will activate or inhibit that other protein. Once this protein changes its activity, has the ability to change the activity of other proteins. And you can simulate like the propagation of a signal over the network using this random walk, for example. That would be a more mechanistic meaning for the random walk. But in practice, people use random walks with restart just to rank the nodes according to their relative similarity or similarity or distance to the original nodes. One advantage extra for this random walk with restarts is that you don't need to compute only the random walk with restart starting at one individual node and then with the end probability distribution. So you can say that node 1 is related with node 4 with a 0.13 strength, node 2 is related to node 4 with a 0.10 strength, and so on. So this would be like a pairwise similarity between the nodes. But you can do the random walk with restart starting at multiple nodes, and you can start at multiple nodes with different weights. So this is very computationally efficient way of computing relationships between sets of nodes. For example, people use this strategy to predict nodes that are associated with a disease. So normally imagine that this is a protein interaction network, and people have previous information that says that node 4, 5, and 3 are disease related. So they are associated with the mechanism of a given disease. And then you do the random walk starting with from these 3 nodes. And then you select after you compute the stationary probability distribution of the random walk with restart, you select the top nodes that are not 3, 4, and 5, but from the rest of the network, what are the other nodes with a higher random walk probability? Those have a higher likelihood of being associated with the disease also. And this is actually an algorithm that has been used to predict genes associated with, to predict new genes associated with a disease. And we'll give more examples of this type of analysis later, if we have time.
Okay, thank you.
Can I ask a question about the formula?
Sure. Yes.
Shouldn't it be that the ranking factor before the equal sign, shouldn't it be I+1 that you calculate?
Yeah. So normally people write this in this way because when the ranking vector gets to the stationary value, you don't need the I anymore. Okay. But you are right. If the iterative process that I described, it should be in this place. It should be I+1. You are completely right. But the aim is to do this iteration until you reach a point where the ranking vector I is equal to, almost equal to the ranking vector I+1. So you can write this equation without the iteration index.
Okay, thank you.
Again, you must be careful because normally the PageRank algorithm that is implemented, for example, in iGraph, uses as a parameter for the random walk with restart the damping factor. So it is this C. Okay. But you can use, maybe using different languages or different tools, the random walk with restart may be parameterized with restart probability. So the formula is different. You have here a P and 1 minus P in this side. Of course, if you are as in this case, if you are parameterizing the method with the damping probability and not the restart probability, then if the damping is closer to 1, in practice, the ranking vector that you will get is more close to the degree distribution. Because if you don't have a lot of restart, it's almost like if the random walk was infinite. It's only infinite if C is 1. But if it's 0.99, you will get a ranking vector that is very similar. So it's highly correlated with the degree vector for all the nodes. If you have a C that is very low, normally what happens is that the random walks are so short that a large part of the network has a ranking value close to 0 or a probability of being visited close to 0. And only in the more close neighborhood of the starting nodes, you get a higher probability of being visited. So normally people work, the most common used value is for C, for the damping factor, is 0.85. It is a value that allows random walks to spread a little bit farther away from the origin, but still you don't get a vector that is highly correlated with the degree. Okay. When you start getting above 0.9, 0.95, then you start getting a distribution of the probability of being visited very close to the degree. But you can choose that. If you are using an algorithm that is parameterized with the restart probability, then the most common parameter is 0.15. But this is empirical. There is no reason why 0.15 restart probability is better than 0.20 or 0.3. Normally, when I apply this, what I look is I plot the. Normally, this is very easy to compute, is quick to compute, so I can compute it for different restart probabilities. And normally, what I want is I want to have values for the most of my network nodes, to have a ranking that includes all the network, but not. But we are still farther from the degree vector. Okay, so it's a balance. I want the random walk to go to visit almost all parts of the network, to have a ranking, an effective ranking for all the network nodes, but the minimum probability, the minimum risk, yeah, the minimum, I'm confused now. So the minimum damping factor, so the minimum damping factor that allows me to have a ranking that goes all through the network, but still is not close to the degree vector. So that's my rule of thumb when I apply a random walk with restart. But it is simply a way to compute a kind of a distance, or in this case, similarity between nodes in the network. More questions about it?
I have one.
Sure.
So when you first started explaining the restart probability, you said that, for example, for node 1, it would have a 0.5 probability of going back to 4, and then 1/3 of going to 4, 1/3 for 3, and 1/3 for 2. Is that what this equation is making? Is it weighting more on the probability of going back?
Yeah, because you have this part of the equation is the part of getting back to the restart. Okay. So when I was presenting that way, I said that the restart probability was 0.5. So C was 0.5, 1 minus C is 0.5. Okay. So with the 50% probability, the next step, you will have the distribution of the starting vector. Mm-hmm. But with the other 50%, the probability of visiting other nodes is defined by the product of the present ranking vector times the weighted agency matrix. And that's why you multiply the vector with the present distribution by the probabilities of changing from one node to one of its neighbors.
Okay, makes sense. But for example, for node 10, how does the restart probability affect it? Because it's not near the start.
The restart doesn't have to be. So wherever you are in the network, wherever the random walker is, if the random choice is for restart, it will go back to the origin.
Oh, okay. Okay. And even if it's not.
Yeah.
Okay.
So this random walk with restart is very similar with the PageRank algorithm that was developed by Google. The difference is that in PageRank was developed to be applied to a network of web pages. And that network of web pages is a directed network, because imagine that 8 is a given web page. It has an arrow going to 9 if this web page has a link that goes to points to the page 9. Okay? Mm-hmm. So it is a directed web page. And the restart is a virtual node that is an artificial node that is not a web page. So the concept of page rank is you have a web surfer instead of a random walker is a web surfer. It's someone that is clicking on links from page to page, but with some probability, it goes back to the original page and picks randomly one of the page to start again. That's the way that Google gives weights to different web pages. And when you do your search, it will order the pages according to this page rank algorithm. But the concept behind is it's the same as a random walk with restart. It just has an artificial external node and the network is directed. Okay.
Okay, thank you.
More questions? No more questions? So once you have relationships between pairs of nodes, it is straightforward to extend those distances or similarities to build communities. So to apply clustering algorithms to those distance matrices or similarity matrices. So you can apply all the clustering algorithms that you apply to analyze other different types of data. So just data that is vectorial in nature. So you have each individual in your data set characterized by a set of variables, and you apply hierarchical clustering or k-means clustering or whatever. You can apply that to a network. Once you have a similarity matrix computed by one of those distances that we talked about, or based on random walks, based on topological overlap, or based on shortest path distances, edge connectivity, so on, you can build the clustering. But usually people in network science have developed alternative methods to find the communities or clusters within the network. So the aim is to break the network, a connected network, into subgraphs that have a modular structure, so that have the property of having a lot of connections within the cluster and not so many connections with the other parts of the cluster. So this is again that concept of modularity. And for example, in this small network, it is clear that you would have 3 clusters or 3 communities, one with these nodes 1 to 4, the second cluster with nodes 5 to 8, and the last cluster with nodes 9 to 12. And that would be reflected, for example, in a similarity matrix constructed with, for example, a shortest path distance. But not all networks are so easily partitioned as this one, and there are different algorithms sorry, I think I had more slides to explain this. So you have different algorithms that allow you to compute the best partition of the network. And yesterday we used in the tutorial two of those methods. So one is the greedy algorithm that simply starts with every node in an individual cluster, and then it joins 2 nodes if by joining those 2 nodes the modularity of the network increases. Modularity being computed as a normalized fraction of the intra-module edges divided by the total number of edges, but normalized for a random network. And you keep doing that, joining nodes until you reach the maximum modularity possible. So you cannot be sure that you reach the maximum modularity possible, but it's an heuristic to get an answer that possibly is close to the maximum, to the absolute maximum of modularity. Sorry. But other strategies are, for example, compute the edge betweenness for all the edges in the network, And so edge between us is similar to node between us, is counting how many times an edge is part of a shortest path linking all other nodes in the network. And in this case, it is obvious that these edges 4, 5, 1, 12, and 8, 9 would be the edges with the higher betweenness. And in that second edge betweenness method, what you do is that you start by deleting the edges that have a higher betweenness, then recompute the edge betweenness, and keep removing edges with higher betweenness until you don't get an increase in modularity, until you start degrading modules instead of separating modules. But there are different alternatives. There are methods based in simulating physical processes like percolation in networks, try to find communities. There is a large list of algorithms that you can use. And as I said yesterday in the tutorial, as with common clustering, each data set, in this case, each network, can be better partitioned with different algorithms. So you have to try multiple algorithms to get to check what is the best result. If your aim is to get the most modular network as possible. But if you are interested in finding groups of nodes that are closely connected, you don't need to partition all the network. You can use other types of searches, like searching for cliques. So a clique is a subgraph where all the nodes are linked to every other node within the clique. So if I go to the previous slide, so this set of 4 nodes, 1, 2, 3, and 4 is a clique. Why? Because each node 1 is connected to 2, 3, and 4. Node 2 is connected to 3, 4, and 1. So every node in the clique is connected to every other node in the clique. So that is the definition of a clique. So cliques are sets of nodes that are maximally connected within them. And so in biological networks, finding a clique is finding a set of nodes that is probably part of if the network is a protein physical interaction network, a clique normally corresponds to a stable protein complex. And normally stable protein complexes are proteins that to perform their function, they need to be physically associated. But you can also have cliques in other types of networks, in signaling or regulatory networks, and basically all the most common assumption is the nodes that are within the same clique, they should be working together. So they should form a functional module. That's the main concept and why we are interested in finding cliques or clusters. But as we know that biological networks and many other networks, we have an incomplete image of what the network is, demanding that we find cliques maybe too stringent. And so you can find different objects that are not exactly cliques. The most close to it is finding quasi-cliques. So they are not cliques, but they are almost cliques. They are called K-plex sets. And that means that the K-plex is a subset of nodes composed of n nodes. And it is a K-plex if all those n nodes have at least n minus k edges within the set. So imagine in the previous slide, if, for example, I did not have the connection between 1 and 3, I would still be able to call these a one-plex, because it's a set of nodes where every node in the set has at least 2 connections to other members of the node. And as the node is composed of four nodes, and by being the maximum possible connectedness would be for every node to have 3 links. And if I don't demand every node to have 3 links, but just 2, I have a 1-plex. No, sorry, I'm saying it wrong. If a 1-plex is a click, because a 1-plex is the set is has 4 nodes. So if I demand all nodes to have 3 links within the set, it's a click. But if I demand every node to have n-2 links, then it is a 2-plex. I demand that every node has at least 2 links to other nodes in the set. Okay. If I ask for a 3-plex, then it's n-3. I start getting more not so dense sets of nodes. Okay, so I'm getting not so stringent in the definition of a set of highly connected nodes. But when you look only at 4 nodes, it is more common to find clicks. But if you look at sets of 10 or 15 nodes, it's very hard to find a click. But it's eventually more common or more easy to find a 3-plex or a quasi-click with not so close to a click, but still a subset of nodes with a high degree of interaction. Was that clear what is a k-plex? Yes? So it's almost a click, but you don't demand that every node is connected exactly to all other nodes in the click, but to a smaller subset of that set of nodes. K-cores are a different way to define the subgraphs that are very densely linked. So in K-cores, what you do is you start with the full network, and then you try to find subgroups of nodes that have at least every node in that subgroup, in that connected subgroup, has at least k interactions. Okay? So the full graph is a 1-core network. Because if the graph is connected, if the graph is connected, every node in the graph has at least 1 interaction. So at the minimum degree in the graph is 1 if the graph is connected. So the 1 core of a network is the actual graph, the original graph. But the 2 core is like you delete interactions to nodes that only have 1 interaction. So those nodes become isolated, and you may become with just a single component of all nodes have more than 2 interactions, or you can start having isolated components, but within each component, every node has at least 2 interactions. Then you go to 3-core, and you get even smaller parts of those components being defined. And as you increase the k-coreness, you get subsets of the graph that have a more dense number of interactions. Okay, that's another way to find really dense subgraphs. Dense in the sense that they have a lot of interactions between its members. Question?
Yes, please. Thank you. When you delete the nodes that have less than k interactions, the subgraph, this could also influence the connections of other nodes, right?
Yes.
And
so it has to be after. So you have the thing is you have to find the subgraphs that have that rule. Every node in the subgraph has at least k interactions within that subgraph. So some of the nodes have a degree of 3, but one of those interactions was with the node that is isolated in the k-core. So in I said a degree of 3. Yeah, so I had the node with a degree of 3. He had 3 interactions. Eventually, it could be part of a 3-core subgraph. But maybe it is not part of a 3-core subgraph, because in the process of getting to from 1 core to 2 core, one of its interactions was lost because it was an isolated node that was deleted because it had only a degree of 1.
Okay.
Does that answer the question? So the minimum number of interactions is within that core. That's important.
Okay.
Yeah. So why are we interested in these? Because dense clusters of subgraphs suggest that we have functional groups of nodes, either protein complexes or small circuits of gene regulatory interactions. But having a dense subcluster is potentially important for the functioning of the system. And eventually it is, as we are trying to analyze sometimes very complex systems with a lot of components and interactions, finding these dense subclusters are like subsystems that we can contain in one capsule. So those sets of nodes are so interconnected that we can treat them as if they were a single node and study the dynamics of that system within that cluster and analyze the larger subsystem as if those dense subclusters were a unit or a subsystem. So that's why it is sometimes important to find these cluster and communities. We talk about this. This is out of order. So you can use to find the clusters. You can use a distance measure and apply a normal clustering algorithm. I said it before. Or this is the stepwise agglomerative is the description of the greedy algorithm that finds the partition that maximizes modularity. And this is the description of the edge between us algorithm to find the best partition. So it deletes node edges with high betweenness, and in that way finds the communities with larger modularity. So, but that was before. So before the cliques and all that out of order slide. Basically what we described is with local properties, we can characterize each node individually by centrality measures. We can quantify the relationship or the degree of interaction between pairs of nodes by shortest path distances, topological overlap, edge or vertex connectivity, with the random walks or diffusion metrics. You can relate pairs of nodes in the network, or you can find clusters or modules in the network. So why is that useful in numbers? Numbers quantifying the abundance of a component. I don't know if you are listening correctly, because I had the sign that the network was unstable.
Yeah,
I didn't get anything.
Yeah, me neither. Like for 30 seconds.
Yeah, if you could repeat the last part.
What can we do with networks?
Basically.
Okay. So the idea is that you can use these measurements in networks to better analyze and extract knowledge from results from omics-style experiments, like transcriptomics, proteomics, and in those experiments you quantify in parallel a large set of proteins in your sample, or the gene expression of virtually all the genes in your system, and so you have numbers that you can attribute to the nodes in the network. Okay? And in that way, you can try to identify parts of the network that are more active or more inactive in this experimental situation that you were studying. So that allows you to make an experiment, make a perturbation, see which proteins or which genes or which metabolites change their abundance. Normally, it's that is what is measured. And then look at the network, integrate those values that you have one value per gene or per protein, and look at those numbers in the network and check it's like giving a weight to the nodes, and then check, recompute, for example, distances taking into account those nodes between pairs of nodes, or finding clusters that are not only densely connected, but they accumulate a lot of high abundance nodes, or nodes that are changing their abundance from the control versus the perturbation group of results. So you map your results on the network, and then try to identify within the network what is the subsystem that is more affected by that experimental perturbation. And then look at the annotations of those genes, and check what they are doing, or what is known about what they are doing, and analyze your results from using that. So this class of methods, that once you have quantitative values for every node in the network, and tries to identify modules in the network that accumulate a lot of either change or abundance in those results, is a class of algorithms called active module detection. And if I have time, I'll show you one of that was very recently published. Sometimes you don't integrate the quantitative measurements, but you perform some kind of a test, statistical test, and detect a sublist of genes, proteins, or microRNAs or messenger RNAs that are significantly differentially expressed according to conditions. And then you want to look, where are those differentially expressed genes or proteins in your network? Are they very close to each other? Are they just form one unique module, or are they spreading, organized into multiple modules? So you want to extract the connected subnetworks containing your differentially expressed genes, and study what's their relationship. Maybe you find out that, yes, you identified, for example, if you are studying a gene regulatory network where the interactions are the transcription factor and the targets, or the microRNAs and their targets, and you have an experiment where you found a list of differentially expressed proteins or genes, for example, and by finding that a lot of them are within the same module in the regulatory network, you can, and in a regulatory network, it should be a directed network, you can spot or try to identify within that module what was the origin of that changes, because some of the changes that you are seeing are not directly caused by the experimental perturbation, but once you change the expression of gene A, that change in expression will cause changes in expression in adjacent genes in the network. So you can try to interpret the changes that you are seeing in the experiment, and propose a mechanistic explanation for those changes, if you are working with regulatory networks. But if you are working with protein-protein interactions, we are just seeing that the genes that respond together to the perturbation are also genes that interact physically, and there may be a functional explanation for that co-response between those sets of genes. And if you, for example, have that list of candidates, and you extract the minimum subnetwork that contain all your interesting genes, and that is solved with the Steiner's 3 problem. Yesterday in the tutorial, there was a function called joint comp, that exactly what that function does is implementing the Steiner 3 problem, or a solution for the Steiner 3 problem. And this problem is, you have a network, and you are interested in studying, in getting the minimum size subnetwork that contains all your interesting candidates in a connected subgraph. So you have to, that connected subgraph has to include your list of candidate nodes, plus the minimum set of nodes that makes them a connected subgraph. That is an optimization problem, and there are different approaches to it, but that joint comp function implements one of them. And once you have this subnetwork, you can try to identify which modules in that you can divide it, further divide it into modules, which are the modules that are more affected, which ones have higher differences in expression, for example. The pattern of changes that you see in those genes means that the communication between functional modules is disrupted or not. Among those affected genes, what are the most important in that subnetwork? So you can apply the centrality measures to identify which of those affected genes probably are are more directly linked to the cause of the changes that you are seeing. So these are different things that you can do with the networks. You can also use instead of using the networks to help you analyze experimental results. Sorry. Sorry. You can use the available networks to generate hypotheses that you can study after. So, and one common approach is trying to predict functions for nodes in the network using generally what is called I missed the name now. So it basically is if your node in the network, you don't know the function of a given node in the network of a protein. It's not annotated, but it has 5 neighbors in the network and 4 of them are involved in apoptosis. So it's very likely that that node is also involved in apoptosis. Okay? So it's using that, I remembered, it's guilt by association principle. So it's like you can infer the function of a node by looking at the function of the people who hangs out with it. In this case, the network neighborhood. And this principle is used, for example, to predict genes that are associated with a given disease. It can be used to, there are some proteins that are already known to be drug targets for a given disease. But if we find using network data that that drug target is also very close or very connected, very well connected with genes associated with a different disease, maybe we can propose that that drug can be applied to a different disease than the one originally, for which it was originally developed. So we can try to find, we have 2 different diseases that have some phenotypic similarities. Can we find the nodes in the network that are responsible for that phenotypic similarity? And I'm always talking about diseases because my research is more close to that side, but you can substitute the word diseases in these sentences by a complex phenotype. So you may not be interested in studying a disease, but you may be interested in studying a phenotype in your organisms of study, or a process that you are interested in studying and that is carried by a group of proteins or genes. And normally these groups of proteins that work together to achieve some phenotype are close by in the network. So we use the network to expand our knowledge about the plane going down. To explain our knowledge about the mechanism behind those complexes, those phenotypes or those diseases. So in the last 5 minutes, I have a few examples. I'm not sure if I'm going to present all of them. So, but this was published, it was accepted in November 2020, but came out already in 2021. And it is probably one of the most recent versions of the active module identification algorithm. And just to show you how it works. So you have a network, and the idea here is that from that experiment, from that omic experiment that you have, there are some nodes that have a higher abundance or that change their expression or their activity in the experiment. And what you do is you first, without knowing which are the nodes in the network that have a stronger signal in your experimental results, you divide the network into modules. In this case, they shows a low-vein modularity algorithm that is also available in iGraph, is one of the cluster functions. So you can implement these in iGraph. So you divide the full network into what they call slices, but these are equivalent to modules. And then you evaluate each of the slices if the number of genes with a significant change in expression, for example, is highly prevalent or not. And how do they do this? They use a hypergeometric test that is that is an enrichment test. So it asks the question. So in this small slice, I have 1, 2, 3, 4, 5 nodes. And within those 5 nodes, I have 2 that have a significant result in the omics experiment. So my question is, I know that in the full network, I have 1, 2, 3, 4, 5, 6, 7 red nodes. So what is the probability if I pick by chance 5 nodes from the full network? What is the probability that I get 2 red nodes or more? If that probability just by chance is very low, it means that it is a rare event to observe a subset of 5 nodes with 2 nodes significantly change in their expression, for example. And this is computed by a hypergeometric test, and gives you a p-value. The p-value is corrected due to multiple testing issues. And then you get a key value that is already corrected, and you select the modules that are enriched in nodes that have a significant result in your experimental results. Then, within those selected modules, you apply what is called this PCST. That is in the paper, it is a prize collecting Steiner 3 problem. So the idea is that I want to define the minimal subnetwork that includes these significantly changed genes. But it is the prize collecting is that it selects the other nodes that are connecting these significantly changed genes, selecting the ones that have a higher signal in the experimental results. So each node has a value coming from the experimental result, change in expression, for example, and it tries to build the minimal subnetwork within this slice that contains the significantly changed genes and includes the minimum set of other genes that also have the highest possible changes in the experimental results. Maybe not significant, but the highest possible changes. And if after performing this prize collecting Steiner 3 algorithm, you still have a large cluster of genes, and by large they say that if you get a subnetwork, they call this a subslice, that is larger than 10 genes, then you apply again a clustering algorithm to find submodules within this subslice. And in the end, you reevaluate if these submodules or these subslices are enriched in significantly changed genes, and that's your end result. The active modules would be this subslice, and within this slice, this sub cluster would be the results of the active module identification. Okay. Any question? No. So I'm not going to present the other ones, but this is another set of methods in using network medicine approach, that is network biology applying to the study of diseases. And eventually what I can do is I can even if you have to leave, I can save it and then you can check the video after. That would be an hypothesis. But before, if you have to leave, if there is any doubt, any question that you didn't understand, I always make this mistake in English.
No, thank you. I'm leaving.
Okay, sure. You can leave. I will keep presenting. You can all leave if you want. I will keep presenting to be in the same video. Okay.
Yeah, I also have a class now, but thank you.
Thank you. Bom dia.
Adeus, bom dia. Okay. So, I don't know if other ones are staying. Are you?
Yeah, I'm staying.
Okay. But you are not, if you have other classes, you can.
I don't.
Okay. So in particular, these kind of methods have been applied in a field called network medicine. And this is the definition of network medicine according to this Network Medicine Institute that was recently formed that aims to promote this scientific area. So network medicine combines principles and approaches from network sciences, systems biology, and human dynamics. I don't know exactly what they mean by human dynamics, but to understand the causes of human diseases and develop new treatments. If you can consult here the network medicine site, and it has an history of network medicine and some links to groundbreaking papers in this area if you are interested. So the basic principle here is that we can use networks, so that is the pattern of interaction between proteins or genes in cellular networks, in biological networks, to understand the causes of disease or to propose a new therapeutic mechanism or understand a currently available drug, how it works in that particular disease. So the idea here is that many diseases, particularly the ones that have a genetic cause or have genetic modifiers, not exactly the cause, the disease may be caused by other external environmental factors, but many people have genetic variants in their genes that make them more susceptible to the development of that disease, for example. So many diseases have genes that are known to be causal for that disease if mutated, or genes that modify the susceptibility of an individual for a given disease if that individual has a sequence variant that has an impact on the function of that gene. In particular, they have found that a lot of mutations that that are associated with the development of disease or the modifying the phenotype of some diseases are mutations that do not delete or decrease significantly the function of that gene or of the product codified by that gene, but even you can have a change in an amino acid that is in the interface of that protein and will change the physical protein interactions that that protein has. And we call these mutations agetic mutations. So it is a mutation that doesn't change for example, the catalytic center of the protein, but changes the interface of the protein to contact with other proteins. And that may be relevant because these physical interactions with other proteins may be important for that protein to perform its function correctly in the right site in the cell with the right targets, or it needs to be anchored at some part of the cell, or it needs to acquire a different conformation after the formation of a protein complex, for example. So there are a lot of mutations associated with disease that are agetic mutations. They change the pattern of interactions of the associated protein. But of course, you also have some disease-causing mutations where the mutation leads to either the misfolding of the protein, so the protein is not functional, or the protein is not even synthesized because it has a premature stop codon. Things like that are very common in disease-causing mutations. So you have these two mechanisms, but what leads that perturbation in one node of the network to have a systemic effect, disease phenotype, can be explained by the spread of that perturbation throughout a biological network. So that's the principle of how can we use the networks to understand how the mechanism of the pathological phenotype is developed. It is also possible to knowing drug targets. So you know that this drug binds to a given, for example, protein kinase, that is a very common drug target or a receptor. And using the network of biological interactions, we can check how perturbing these nodes in the network will affect other nodes that we know are associated biologically, because we already know the function of that gene that is associated with a phenotype of that disease, for example. So we can try to explain how a drug has a significant effect on that disease using network biology. So the aims of network medicine is to use the available information about transcriptomic networks, proteomic networks, metabolomic networks, but they include also here, this is that part of the human dynamics. So where you have clinical phenotypes for populations of individuals and other factors that may affect, external environmental factors that may affect disease. And you want to use those networks with these kind of network algorithms to improve our understanding of the mechanism that generates the disease. Some people are interested in reclassifying diseases. So traditionally, diseases are classified according to the tissue or the organ that is affected, the types of symptoms or signals. And here, a group of people, including this researcher Los Calzo, is very interested in reclassifying diseases according to the molecular signature of that disease. And the aim is to use this information either to prevent disease by identifying factors that are risk factors for disease and trying to avoid the effect of those risk factors, and develop new therapies. And this part of developing new therapies is associated with the concept of precision medicine. So this is in the future somewhere, we will have the ability to perform some of these multi-omic molecular analysis to each individual, either when it is disease, it is suffering from a disease, or even before when it is healthy. But by performing this kind of data extraction, you get information that makes that individual unique. It has unique characteristics that you can detect through these multi-omic analyses. And to make sense of these omics data, we are going to map these results in a network of biological interactors, a protein-protein interaction network, or multi-layers of protein of biological network interactions. And in this way, we will tailor this common network that is, for example, a human network. We'll tailor it for this individual. So we'll change the network. Some of the nodes are more active, some are more inactive, some are not there in that individual, or are mutated. And each network may be different for each individual. And then we can use that information to have a better connection between the genotype and the phenotype in that individual that is dependent on this network. They call it the reticulotype of the individual, and that may be helpful to choose the correct therapy for that individual. So the idea is that we don't use the same therapy for every individual with the same disease, but we have to adapt therapy to particular individuals because some drugs work better in some types of individuals and not in others. This is already ongoing, so there are people studying genetic factors that make some groups, some population groups more susceptible to some diseases or to where some drugs are not so much effective. But here the idea is that use the network knowledge to take more advantage of the omics data for that individual. So in particular, so this is like my propaganda part of the lecture. I have been working in this area, and one of the works that we developed was developing an algorithm called specific betweenness. So S2 is because it is doubly specific betweenness. And we applied this method to cross-disease analysis. So the aim is to find candidate proteins that are simultaneously involved in more than one disease, and especially in pairs of diseases with phenotypic similarities. And the idea is that those proteins could be potentially new drug targets or could explain the mechanism by which those two different diseases have similar phenotypes. So this method originated from previous knowledge, some previous hypotheses. So we already knew that disease genes, so disease genes that are associated with a given disease, and the association with the disease does not mean that the gene is causal to that disease when mutated. It may be that the gene is associated with disease because it is a biomarker, or it is a gene that has been observed to be differentially expressed in the disease tissue versus the normal tissue. And nowadays there are databases that collect that kind of information of disease-associated genes. And people have observed that in molecular interaction network, like for example, protein interaction networks, those disease genes associated with the same disease tend to occupy a limited neighborhood of the network. So they are concentrated in a network region and define what is called the disease module. And it has already been observed that different diseases may have an overlap between their disease modules, especially if the diseases are somehow related. For example, in this example, we have multiple sclerosis, peroxisomal disorders, and rheumatoid arthritis. And the thing is that peroxisomal disorders are not related with the other two, while multiple sclerosis and rheumatoid arthritis are both related with the autoimmunity processes. So these two disease modules are very interconnected and have overlap. So there are some nodes that are associated with both diseases simultaneously. But another disease that is unrelated in terms of mechanism or phenotype doesn't have that overlap. So they are more separated in the network. So we try to use that knowledge that diseases tend to form disease modules in networks, and that related diseases share more disease-associated genes. And as we know that both networks and the list of disease-associated genes are incomplete, it would be useful to get new candidate genes to be associated with diseases. And we thought that it would be particularly informative to discover candidate proteins that would be associated with two diseases simultaneously. So our hypothesis was that those diseases with common phenotypes have an overlap between their disease network modules. And the hypothesis is that the nodes that are in the overlap between the two disease modules, in this case, these two blue-red nodes, should be parts of shortest paths linking nodes from one disease to nodes of the other disease. So if I want to connect this red node to this blue node, the shortest path must go through the overlap. Here to there, here to there. So the genes that are in the overlap should that's our hypothesis, be more frequently in part of shortest paths linking nodes from one disease to nodes on the other disease. So this concept is highly similar to the betweenness centrality, but the betweenness centrality is computed for the whole network. So we want to measure how many times a node is part of the shortest path, linking all network nodes. Here we are particularly interested in shortest paths connecting nodes from one disease to nodes of the other disease. So we use a specific version of the betweenness to rank candidate genes. So the difference is that in standard betweenness, we compute the fraction of shortest paths that the node takes part in all network shortest paths. But now we are only interested in shortest paths connecting disease-associated genes. But we know, as I said previously, that some nodes have a high betweenness just because they have a high degree. So they should present a high betweenness to any pair of to any set of nodes, not particularly to those diseases. So we want to take out from our predictions some nodes that will appear everywhere because they are densely connected, because they have a very high degree. So how we do that? By randomizing the network. So we build randomized versions of the network by changing who is connected with other node, but maintaining the number of nodes and the number of interactions that each node has. So we keep the degree of each node. In this way, the nodes with a high degree will keep popping up as top betweenness nodes, even in the randomized networks. And the ones that we are more interested are nodes that have a high betweenness, even only in the real network. And when you randomize the network, you lose that property because you are not analyzing anymore the specific disease-associated genes of the two diseases that you are studying. So that's how we select our specific betweenness nodes. So whenever you propose a method like this, you have to show that the method works. And here we demonstrated that the method works using artificial disease models. Why? Because so real disease models are incomplete, so we don't know their full composition, and so we don't know all the overlap genes between two disease models. And to get around that, we built artificial disease models. So we started in one node in the network, and we expanded to the neighborhood region of that network, and we called it a disease model, an artificial disease model. And we built multiple of those disease models with different origins, and then selected pairs of artificial disease models with an overlap. Then we randomly selected a fraction of the nodes in those artificial disease models, not including the nodes in the overlap, and applied the method to check if the top ranking has to be genes or have to be nodes where the overlap genes that we had hidden from the method. So these are the results. We evaluated the fraction of nodes that were in the top of our ranking that were effectively in the overlap. So this is equivalent to precision measure. So we see that the precision for if you select as positives, only for example, the top 25 genes, we get a precision that is close to 80%. So 80% of our candidates are in fact in the overlap. We have different colors here because we tried different shapes of the disease models, of the artificial disease models. So the mechanism to generate the models was different. One was using random walk with restart, the other used the connectivity algorithm, and the shell is just defining that the artificial disease module is the causal node and all the nodes that are at a distance of two edges, shortest path of two. So it includes the direct neighbors and the second, the neighbors of your direct neighbors, the second set of neighbors. So these are the simplest ones. and you have different types of ways to build the artificial models. And you see that once you include more candidates, you lose that precision. But if you consider that you are interested not only in the genes that are in the overlap, but if you find candidates that are direct neighbors of genes in the overlap, you are also satisfied because you are locating in the network where that overlap is, then we get very high precisions across a larger number of candidate rank tops, excluding the connectivity modules that are not so successful. And we also evaluated the recall that is among the list of candidates. So among all among all the known genes to be in the overlap between the two disease modules, what's the fraction of those positive overlap genes that you recovered with your predictions? That is the recall, and you see that the recall increases quite rapidly as you increase the candidate rank and reaches like around 80% recall for between 150 and 200 top candidates. So we were happy with these results, and we also compared it with the. At the time, there were no available methods to make this type of prediction because there are a lot of algorithms to predict genes associated with a single disease, not with a pair of diseases. We also evaluated if our method was robust to perturbations in the input information, either the number of seeds, so these values were using only 50% of the genes associated with the disease module, as a sampling from the total disease model, only 50% of the members, and using them as input to the method, or using a smaller amount of seeds as inputs, and you get similar performance in terms of precision. You can add artificial random edges to the network, so noise in the network. So we are assuming that some of the nodes in the network are false positives, so they are not real interactions. So we add false interactions and see what happens in the predictions. So some of the predictions decrease a little bit, but not very significantly. And we also introduced genes associated with the diseases that were not actually part of the disease model. So we selected random genes to be part of the disease models, and our method is robust in part because we are only selecting the genes that are in the overlap, that are many times in shortest path linking the two disease modules, and this fraction of random seeds was not enough to balance and probably the shortest paths linking these random seeds were scattered around the network, so they wouldn't affect the ranking of our top candidates. We applied this method to study two diseases, ALS, that is amyotrophic lateral sclerosis, and SMA, spinal muscular atrophy, and found the subnetwork that contained the top ranking S2B genes. The size of the nodes is proportional to the S2B score. Within this network, we identified cliques because we found large cliques in these networks and tried to check if these cliques were specifically associated with some of the phenotypes associated with both these diseases. These two diseases affect motor neuron cells. And we also identified these clusters, identified by color, that were genes that frequently appear together in the shortest paths linking the two diseases. So we get these clusters, and we analyzed functionally these clusters because there was for most of them previous evidence that these genes were associated with mechanisms that are common to both diseases. We wanted also to validate our predictions with external evidence, not only with the
artificial disease modules. And in this particular case, we looked for different independent sources of information for genes associated either with ALS, SMA, or with both, and check how many of those genes that were not present in our sources of disease-associated genes. We used the OMIM database and the DGNet database. So of course, there was some overlap between these databases and these other sources. And we took out the ones that were present simultaneously in both sources. And the ones that were uniquely present in open targets, for example, we could find around 1,300 genes associated with ALS. 44 were among the 206 S2B candidates, and the remaining were in the rest of the network. But when we compare if finding 44 in 206 out of the total number in the full network, it was not randomly expected to get such a high number. And we actually had a frequency of the ALS genes in the candidates that was around 2 times more frequent than expected by chance. For SMA, it was around 3 times more frequent than expected by chance. And for genes that, according to open targets, were both simultaneously related to ALS and SMA, we get 4.5 more frequent frequency of these double associated genes than expected by chance. So this is what the method was designed for, to specifically predict genes that were simultaneously associated with both diseases, and using independent sources of information we could check these. This was also valid for the diseases database, where we have an enrichment of 3 for ALS, 12 for SMA, and 53 times more frequently for both, although this is obtained with very small numbers. And we also conducted a very naive text mining approach, where we selected PubMed abstracts that contain both the designation of the disease and the designation of a gene, and selected genes that appeared in abstracts of ALS, in abstracts of SMA, and genes that appeared both in abstracts of SMA and ALS. And again, we get an enrichment in the frequency of these genes in our candidates that is higher, the enrichment for genes involved simultaneously in both diseases. So we're very happy with these results. Any questions about this? No? And this is another example of a network approach to study, in this case, cystic fibrosis related genes. So cystic fibrosis is a disease caused by mutations in the CFTR gene, that is a chloride transport membrane channel, chloride channel that is a membrane protein. And the problem with the CFTR is that these mutations either don't allow the protein to get to the plasma membrane where it is where its function is executed, or once it gets to the plasma membrane, it doesn't transport efficiently chloride, so it is the gating of the channel is not perfect, or the protein is very unstable in the membrane and it is endocytized and degraded. And a group of collaborators in our research center, BioEasy, there is a big group studying cystic fibrosis in BioEasy. So they have different previous evidences of mechanisms that could help to stabilize CFTR, mutated CFTR at the plasma membrane. So one of the groups studied a kinase, a protein kinase called SIC, that is able to phosphorylate CFTR, and once CFTR is phosphorylated by SIC, its endocytosis is promoted. So if we can block the phosphorylation of CFTR by SIC, maybe we can improve the stability of CFTR in the membrane. So that's one of the approaches. The other was involved this NERF1 protein that is what is called the scaffold protein. Is a protein that one of its main known functions is to anchor other proteins together. And in this case, NERF1 is known to bind CFTR at the plasma membrane, and this other group characterize this pathway where an external signal activates a pathway involving the formation of the degradation of PIP2 that activates another protein called esrin, and esrin makes also links with NERF1 and links this complex CFTR NERF, links it with the cytoskeleton. So it anchors the CFTR cytoskeleton, and in this way also allows a longer retention of the CFTR channel in the plasma membrane. Finally, other group in BioEasy studied another mechanism of stabilizing CFTR in the plasma membrane. In this case, it is known that CFTR is activated by cyclic AMP signaling. And one of the ways that CFTR is activated by cyclic AMP signaling is through another protein called EPAC. EPAC1 also binds NERF1, and they have detected that EPAC1 promotes when activated by cyclic AMP, EPAC1 promotes the stabilization of CFTR at the plasma membrane. So they have these three mechanisms that could improve the stability of CFTR at the plasma membrane, and they wanted to ask the question: can we find other proteins that could simultaneously stabilize CFTR at the plasma membrane through multiple of these three different mechanisms? So they performed some parallel experiments where they tried to characterize the protein interactors through co-immunoprecipitation experiments, and then after the co-immunoprecipitation, they identified the proteins by mass spectrometry, and they identified CFTR interactors when they stimulated the activation of esrin and through NERF the stabilization of CFTR at the plasma membrane, and they performed this experiment both with the mutant that is more common in CFTR, the F508del mutation, and with the wild type CFTR, and identified in this case 140 interactors of TFTR, in this case 49, when this esrin NERF pathway was activated. They also identified 47 proteins interacting with CFTR only when EPAC1 was activated, and they also identified proteins that interacted with the CFTR peptide that is phosphorylated with by SIC. So the idea is that we find protein interactors that block the phosphorylation site by SIC. And so they found 20 proteins interacting with that peptide, and 56 interacted with the phosphorylated version of that peptide. So we have these 5 sets of proteins, and we use the human interactor network, so derived from protein physical interaction networks, excluded proteins that are only located in nucleus, mitochondria, or peroxisomes, because we know that CFTR, these interactions that we want to study occur in the cytosol. So CFTR is in the membrane, but these interactions interact with CFTR in the intracellular domain of CFTR. And we wanted to detect other proteins, not these ones, but other proteins that would interact with these lists significantly. So we applied the neighbor enrichment test, that hypergeometric test, and we selected among all the neighbors of each list the ones that had a higher number of neighbors in the list than expected by chance with the hypergeometric test. And then we selected 478 proteins that had more than 2 neighbors in at least 2 of these 5 sets, and were among the 5% of proteins most enriched in neighbors of at least 2 of these sets. So this subnetwork of 478 proteins, we had to narrow it down to the top candidates, and for that we built a subnetwork containing the proteins that we knew that were involved in these mechanisms, from these 478 plus these proteins, we computed the bridge score. I'm going to talk about what is the bridge score. And the proteins with a higher bridge score were selected as candidates for experimental validation. What is the bridge score? So we have this. I didn't notice that this is blocking the slide, but so we have, in this case, for example, for the mechanism involving ESRIN and NRF1 connecting to CFTR. So these 3 proteins interact together. And these are part of those proteins that we identified. And we are going to rank these proteins according to the possibility that these other proteins have to mediate the interactions between these 3 proteins. So the thing is that we list all paths linking NRF to ESRIN, CFTR to ESRIN, NRF to CFTR. So alternative pathways to link them, they are directly linked, but they can also be linked through other proteins. And then we identify other proteins that are frequently part of those short paths. It's not the shortest paths, it's short paths. And we give a higher weight for proteins that are participating paths linking these 3 proteins. Especially, we give a higher weight if it is a short path. In this case, the shortest path possible is, for example, in this case, so this YWAHAZ protein interacts directly with NRF and with ESRIN. So there is a path of length 2 linking these 2 proteins that is mediated by this protein. But this protein also participates in pathways that go from CFTR to ESRIN and from NRF to CFTR. And that's why it has a large size here, because that's the bridge score. The bridge score counts how many times a protein is part of short paths linking these interesting proteins and giving more weight to shorter paths. This approach of the bridging score was used independently in 2 studies to identify candidates for this modulating of CFTR stability. So this was analyzing the individual lists, not the interaction with the integration of the 5 lists, but analyzing each of the lists separately with the bridge score. We were able to identify, in this case, the protein SHC1 that was modulating the impact of SIC on CFTR. And in the case of the NRF-ESRIN interaction, we were able to identify calpain-1, that is this protein here, that was effectively contributing to the stability of CFTR in the plasma membranes. But we wanted to discover proteins that were simultaneously affecting protein stability through more than one of these mechanisms. So we got to a smaller set of candidates. And here you see that for example, this candidate was a specific neighbor. So it was enriched in neighbors of all sets, of all the 5 sets. And it was a strong mediator according to the bridge score between ESRIN, NRF, and SIC with CFTR. And so we used this criteria to select these candidates. Unfortunately, they were evaluated by knockdowns with silencing RNA. And not all of them gave positive results, but at least for some of them, the knockdown was not very efficient. So there was not a big decrease in expression of the gene. But at least for 3 of them, we got significant results. So in fact, these 3 knockdowns were able to increase. So in this case, the steepest the slope. This is a flux iodide flux assay that measures the activity of CFTR, and the greater the slope, the greater the activity of the CFTR. So when you knock down these genes, you get a greater activity than in the wild type. But in the mutant has a very low activity of CFTR. You don't see a big effect of these knockdowns. They behave all similarly to the mutant. But if you add to the mutant a drug that is already available, that facilitates the maturation and the process trafficking of the CFTR protein, and there is more protein in the plasma membrane, because this mutant, the main problem of this mutant is that the protein is retained in the endoplasmic reticulum and does not reach the plasma membrane. So adding this drug that increases the amount of CFTR in the plasma membrane, then you start seeing a smaller effect, but you see some effect of these knockdowns, and particularly this GABARAP G has a significant effect both. So it is this red curve here, has a significant impact in CFTR activity, both in the 508del mutant and in the wild type mutant. So this is I hope that these examples can demonstrate that using these network measurements, we can generate hypotheses that are lead to valid discoveries or to new discoveries about these biological systems. So questions? So this is an extra class. So the people that couldn't be here can look at the video later.
All right, see you next week.
Okay, no questions then.
Thank you. See you next week.
Bye.
Bye.
Bye.